In 2008, NASA embarked on a curious mission to understand how spiders construct their webs in zero gravity. 2 arachnids were selected for this cosmic venture, with one spider taking the lead role and the other designated as a backup, just in case things took an unexpected turn. However, the escapades that unfolded were far from the anticipated script. The backup spider, perhaps feeling a bit too adventurous, managed to liberate itself from its confinement and paid an uninvited visit to its fellow 8-legged astronaut. The consequence? A bit of chaos ensued as they weaved tangled webs that became an intricate interference. As if this wasn't enough, the flies, meant to be a delectable meal for the spiders, decided to outsmart their captors by reproducing at a pace that caught everyone off guard. Their larvae, in an unexpected turn, covered the front window of the chamber, gradually rendering the spiders hidden behind this unexpected curtain of life. Despite the initial setback, the story doesn't end there. Fast forward to 2011, and the same researcher, fueled by curiosity, secured another opportunity to repeat the experiment. This time, lessons learned, they enlisted the help of other researchers and opted for a different spider species. 4 spiders were part of this venture, 2 destined for the International Space Station, ISS, and 2 designated for the familiar pull of Earth's gravity. The aim? To observe how the spiders would behave under varying gravitational conditions. However, a surprising twist awaited the team. What was initially thought to be a group of 4 female spiders turned out to include 2 males. Determining the sex of young spiders can be tricky business, but the unintended gender mix provided an unexpected opportunity for valuable comparative data. Despite this unexpected deviation from the plan, the second attempt proved to be a success. The spiders exhibited remarkable activity, diligently constructing and deconstructing their webs. Even in the absence of the familiar tug of gravity, they went on to spin new webs. The cameras on board captured thousands of images showcasing the industrious work of these space-faring spiders. Intriguingly, the symmetry of the webs created in space exceeded those crafted on Earth. It seemed that the absence of gravity encouraged the spiders to produce webs with a more pronounced and geometric balance, challenging our assumptions about how these arachnids adapt to their cosmic surroundings. In the middle, and surprisingly, the spiders didn't always position their heads downward as they typically do on Earth. However, one significant factor made all the difference: light. When the spiders on the ISS had a source of light, they wove asymmetrical webs similar to those found on our home planet. Light played a crucial role in orienting the spiders in space. The chamber's lamps were attached at the top. If the lights had been positioned differently, for example on the side, it would have been challenging to observe the effect of light on the symmetry of webs in zero gravity. When the lights were turned off, the spiders rested in random orientations within their webs. Yet, with the lights on, they would orient themselves away from the light source, which meant downward. Hence, in the absence of gravity, light assisted them in orientation. This discovery was unexpected because spiders can typically build their webs in the dark and capture prey effectively even without light. A spider's web itself is a fascinating creation. It's like these creatures have small silk production factories inside them. Within their body, a thread is stored in the form of a highly concentrated liquid, and a regular garden spider can produce up to 7 different types of silk, each having a unique combination of proteins. Each type of silk has a different purpose. For example, one type of thread makes the web elastic, which means the web absorbs the impact when insects collide with it. Another type of silk makes the thread flexible and strong, so it's more difficult to break. Some proteins found in the silk protect it from harmful bacteria and fungi, allowing the web to last longer. They also keep the silk moist so it doesn't dry out. Imagine having a home where you don't have to buy anything extra to maintain it. Spider silk is lighter than cotton and incredibly thin, up to 1,000 times thinner than human hair. It's a marvel of nature's engineering, showcasing the intricate capabilities of these small arachnids. Web, it's not just constructing a trap, it's creating a finely tuned instrument. Spider silk's unique properties extend to its ability to detect vibrations. If you've ever observed a spider on its web, you must have noticed how attentively it responds to even the slightest vibrations. Spider silk can be finely adjusted to different sound frequencies, unlike any other material. The silk is not just a passive structure, it actively senses and responds to the environment. This sensitivity to vibrations is crucial for the spider's survival. It helps them distinguish between the random movements of wind and rain and the specific vibrations caused by trapped prey. Imagine the web as a sophisticated musical instrument, each strand tuned to a specific note. When an insect gets entangled, it creates vibrations that travel through the silk. The spider, sitting at the center of its web, can interpret these vibrations, identifying the size and struggle of the caught prey. This allows the spider to quickly assess whether it's worth the effort to approach and capture the prey. This incredible ability to hear through their webs showcases the adaptability and versatility of spiders. It's not just a passive structure, it's an active tool that helps these arachnids thrive in various environments and conditions. It's a testament to the intricate ways in which nature equips even its smallest inhabitants for survival. This sticky situation for the unsuspecting insects. Now, let's talk about the incredible Darwin's bark spider. This remarkable arachnid doesn't just spin an ordinary web, it engineers a masterpiece. Female Darwin's bark spiders are true architects, creating gigantic webs that can stretch over rivers and lakes, reaching over 80 feet across. Imagine the engineering prowess required for such an impressive feat. The purpose of these enormous webs goes beyond the usual insect-catching strategy. It's a genius plan to capture large insects that gracefully fly above the water surface, like dragonflies. The spider's web acts as a bridge, intercepting these insects midair. It's like a carefully designed trap for airborne prey. Constructing such a colossal web is no easy task and takes days of meticulous effort. The spider spans special lines across the river, anchoring the web firmly to each bank. This not only ensures stability but also creates an effective barrier for unsuspecting insects. Once caught in the web, the prey is at the mercy of the Darwin's bark spider. These spiders showcase the incredible diversity of silk use among different species. From tuning silk for vibrations to generating electrically charged poofs, each spider has its unique method. It's a testament to the adaptability and creativity of these tiny architects in the insect world. Nature never ceases to amaze with its ingenious solutions for survival.